Hello everyone, welcome to Swayam course on AI using Prolog. My name is Madhuri Gupta, Assistant Professor, Computer Science and Engineering Department, Chhattisgarh Swami Vivekanand Technical University, Bhilai. Today's our topic is A-star algorithm. Before starting our today's class, let's have a recap on best first search. Best first search is a graph traversal algorithm that aims to explore the most promising paths first based on a heuristic evaluation of the nodes. Here is a brief recap. Best first search is an informed search algorithm that uses a heuristic function to estimate the cost or distance to the goal from a given node. At each step, the algorithm selects the node that is considered the most promising according to the heuristic function, without necessarily considering the total cost of reaching that node. Unlike algorithms like Dijkstra's, best first search does not necessarily expand nodes in order of their actual path cost. Instead, it is driven by the heuristic guidance. The heuristic functions plays a crucial role in determining the order of explorations. Nodes with lower heuristic values are considered more promising and expanded first. Best first search can be very efficient if the heuristic is well designed that accurately reflects the true cost to reach the goal. However, if the heuristic is poorly chosen, the algorithm might not find the optimal solution or may take inefficient path. A common variant of best first search is the A-star algorithm, which combines the advantages of both Dijkstra's algorithm, considering actual path cost, and best first search using a heuristic. A-star aims to find the optimal path by considering both the path cost and the heuristic estimate. Best first search is commonly used in various AI applications including pathfinding, puzzle solving and optimization problems. Remember that best first search is not guaranteed to find the optimal solution in all cases, especially if the heuristic is not admissible. However, when used wisely, it can be a powerful tool for exploring large search space efficiently. So, let us begin with the detailed description of today's lecture, that is on A-star algorithm. Welcome everyone to today's presentation on the A-star algorithm, a remarkable tool that AI user to find the shortest path between 2 points. Let us dive in. So, imagine you have lost in a maze and desperately trying to find the quickest way out. That is the challenge the A-star algorithm can help us to solve. The A-star algorithm uses a combination of two functions, the cost to reach a particular point, the g function, and an estimate of how far that point is from the goal, the h function. Together this form the f function which guides our search. Each node in the maze is like a point on a map and they are all interconnected. We start from the initial point and explore neighboring nodes, calculating their f values. The algorithm then picks the node with the lowest f value and continues the process. As we progress, the algorithm keeps a priority queue of node to explore the next. It prefers nodes with lower f values, meaning they have a better chance of leading us to our goal efficiently. But here is the fascinating part. The A-star algorithm is informed. It uses that h function, often called the heuristic, which is an estimate of how the remaining distance to the goal. This heuristic guides the algorithm towards the goal while avoiding unnecessary detours. You might wonder, how is A star different from Dijkstra algorithm? Well, Dijkstra algorithm explores all nodes equally, focusing slowly on the G function. A star is smarter. It considers both the distance travelled so far and the estimated remaining distance, making it more efficient. Now, let us see A star in action in a more complex maze. As we follow the algorithm's steps, you will notice it intelligently explores paths, discarding ones that seem to lead away from the goal. See how the algorithm balances exploration and exploitation. It consistently works toward the goal while adapting the maze layout, and that's the A star algorithm for you. An AI tool that navigate maze, find routes and efficiently explore the possibilities using a clever combination of path cost and heuristic estimate. So, next time you find yourself trapped in a labyrinth or need direction, remember the A star algorithm and how it uses both wisdom and calculation to guide AI's pathfinding. So, here is the A star algorithm. Step 1, initialize two lists, open and closed. Second, add the start node to the open list with a cost of 0 and initial heuristic estimate h for reaching the goal. Third, while the open list is not empty, A, select the node with the lowest f values from the open list. This is the node to be expanded. B, move the selected node from the open list to the closed list. C, if the selected node is the goal node, the path has been found. Exit. D, generate successors, means neighbors of the selected node. Calculate the G value. G value means the cost from the start node to the successor through the selected node. Calculate the H value, that means heuristic estimate of the remaining cost from the successor to the goal. Calculate the F value. F is equal to G plus H. E, for each successor, if the successor is the closed list, skip it. If the successor is not in the open list, add it to the open list. If the successor is already in the open list and the new G value is lower, update the node's G value and parent. Step 4. If the open list is empty and the goal has not been reached, no path exists. So, A star algorithm is one of the best and popular technique used for pathfinding and graph traversals. A lot of games and web-based maps use this algorithm for finding the shortest path efficiently. It is essentially a best first search algorithm. So, let us have the working of A star algorithm. A star algorithm works as it maintains a tree of path originating at the start node. Next, it extends those paths one edge at a time. Next, it continues until its termination criterion is satisfied. A star algorithm extends the path that minimizes the following function: f of n is equal to g of n plus h of n. Here n is the last node on the path, g of n is the cost of the path from start node to node n. H of n is a heuristic function that estimates cost of the cheapest path from node n to the goal node. So, the implementation of A star algorithm involves maintaining two lists, open and closed. Open means contains those nodes that have been evaluated by the heuristic function but have not been expanded into successor yet. Closed means contains those nodes that have already been visited. And the algorithm is as follows. First, define a list open. Initially, open consists solely of a single node, the start node S. Step 2, if the list is empty, return failure and exist. Step 3, remove node n from the smallest value of f of n from open and move it to list closed. If node n is a goal state, return success and exit. Step 4, expand node n. Step 5, if any successor to n is the goal node, return success and the solution by tracing the path from goal node to S. Otherwise, go to step 6. Step 6, for each successor node, apply the evaluation function f to the node. If the node has not been in either list, add it to open. Step 7, go back to step 2. So, this is all about the algorithm, another algorithm. So, now practice some of the problem based on A star algorithm. So, problem 1. Given an initial state of a 8 puzzle problem and final state to be reached. So, here we have the diagram which is having the initial state and the final state. Our goal is to find the most cost effective path to reach the final state from initial state using A star algorithm. Consider G of n is equal to depth of node and H of n is equal to number of misplaced tiles. The solution. A star algorithm maintains a tree of paths originating at the initial state. It extends this path one edge at a time. It continues until final state is reached. So, now we have one problem of 8 puzzle problem and we can solve this by using A star algorithm. Here we have initial state where we have the tiles arrangement as 2, 8, 3, 1, 6, 4 and 7 blank 5. So, here we have G is equal to 0, H is equal to 4 and F is equal to 0 plus 4 is equal to 4, because here G is equal to 0 because it is an initial state. So, we have here we have 3 options. First, the next one is 2, 8, 3, 1, 6, 4 blank 7, 5. So, here we have G is equal to 1, H is equal to 5. So, we have F is equal to 1 plus 5, that is 6. So, our next option is 2, 8, 3, 1 blank 4, 7, 6, 5. So, here we have G is equal to 1, H is equal to 3. So, our F is equal to 1 plus 3, that is 4. And we have another option 2, 8, 3, 1, 6, 4, 7, 5 and blank. So, we have G is equal to 1, H is equal to 5. So, our F is equal to 1 plus 5 is equal to 6. So, after getting all the F value, we will go with the minimum value. So, our minimum value is 4. So, we expand that node. So, in this way we have 3 successor. So, we have 2, 8, 3 blank 1, 4, 7, 6, 5. So, we have G is equal to 2, H is equal to 3. So, our F is equal to 2 plus 3, that means 5. and in our next tile we have 2 blank 3 1 8 4 7 6 5. So our G is equal to 2, H is equal to 3. So F is equal to 2 plus 3, that is 5. Next we have 2 8 3 1 4 blank 7 6 5. So our G is equal to 2 and H is equal to 4. So our F is equal to 2 plus 4 is equal to 6. So now we have two options here by using F is equal to 5. So we have tiles like blank 8 3 2 1 4 7 6 5. So our G is equal to 3, H is equal to 3. So F is equal to 3 plus 3, that is 6. And in the next option we have 2 8 3 7 1 4 blank 8 5. So our G is equal to 3, H is equal to 4. So F is equal to 3 plus 4, that is 7. So in our next option we have blank 2 3 1 8 4 7 7 6 5. So our G is equal to 3, H is equal to 2. So our F is equal to 3 plus 2 is equal to 5. And here we have next neighbor, that is 2 3 blank 1 8 4 7 6 5. So our G is equal to 3, H is equal to 4. So our F is equal to 3 plus 4 is equal to 7. So we will move from the minimum. So we have H is equal to 5. So we expand the next node. Here 1 2 3 0, then 8 4 7 6 5. So our G is equal to 4, H is equal to 1. So F is equal to 4 plus 1 is equal to 5. Now expand the successor. So we will get 1 2 3 8 blank 4 7 6 5. So that is our G is equal to 5, H is equal to 0 and F is equal to 5 plus 0 is equal to 5. That is our final state. And we have another option, that is 1 2 3 7 8 4 blank 6 5. So here we have G is equal to 5, H is equal to 2. So our F is equal to F plus 2 is equal to 7. So we have selected our minimum cost final state. So the number written on edges represent the distance between the nodes. The number written on nodes represent the heuristic value. So our goal is to find the most effective path to reach from start node A to final state. So finally, after explaining all the steps, we have found our solution, in which in step 1 we start with node A, node B and node F can be reached from node A. A star algorithm calculates FB and FF. So FB is equal to 6 plus 8 is equal to 14. FF is equal to 3 plus 6 is equal to 9. Since f of f is less than f of b, so it decides to go to node F. So our path is A to F. Step 2, node G and node H can be reached from node F. A star algorithm calculate f of G and f of H, where f of G is equal to 3 plus 4, 3 plus 1 plus 5 is equal to 9, and f of H is equal to 3 plus 7 plus 3 is equal to 13. Since f of G is less than f of H, so it decides to go to node G. So our path is A to F to G. Step 3, node I can be reached from node G. A star algorithm calculate f of I is equal to 3 plus 1 plus 3 plus 1. So total value is 8. It decides to go to node I. So our path is A to F to G to I. Step 4, node E, node H and node J can be reached from node I. A star algorithm calculates f of E, f of H and f of J. F of E means 3 plus 1 plus 3 plus 5 plus 3, that means 15. F of H is equal to 3 plus 1 plus 3 plus 2 plus 3, is equal to 12. F of j is equal to 3 plus 1 plus 3 plus 3 plus 0. The total value is 10. Since f of j is least, so it decide to go to node j. So our path is A to F to G to I and to j. This is required shortest path from A to j. So we have solved this problem. So our important note about this problem is, it is important to note that A star algorithm is one of the best path finding algorithm, but it does not produce the shortest path always. This is because it heavily depends on heuristic. So after solving the two problems, let's have the definition of A star algorithm. It is searching algorithm that is used to find the shortest path between an initial and final point. It is a handy algorithm that is often used for map traversal to find the shortest path to be taken. A star was initially designed as a graph traversal problem to help build a robot that can find its own course. It still remains a widely popular algorithm for graph traversal. It searches for shorter paths first, thus making it an optimal and complete algorithm. An optimal algorithm will find the least cost outcome for a problem, while a complete algorithm finds all the possible outcomes of a problem. Another aspect that makes A star so powerful is the use of weighted graph in its implementation. A weighted graph uses numbers to represent the cost of taking each path or course of action. This means that the algorithms can take the path with the least cost and find the best route in terms of distance and time. So in this figure we have weighted graph. A major drawback of the algorithm is its space and time complexity. It takes a large amount of space to store all possible paths and a lot of time to find them. So our application of A star algorithms. The A star algorithm is widely used in various domains for pathfinding and optimization problems. It has application in robotics, video games, route planning, logistics and artificial intelligence. In robotics, A star helps robot navigate obstacles and find optimal paths. In video games, it enables NPCs to navigate game environments intelligently. Route planning application use A star to find the shortest or fastest routes between locations. Logistic industries utilizes A star for vehicle routing and scheduling. A star is also employed in AI systems such as natural language processing and machine learning to optimize decision making processes. Its versatility and efficiency make it a valuable algorithm in many real world scenarios. So why A star search algorithm? A star search algorithm is a simple and efficient search algorithm that can be used to find the optimal path between two nodes in a graph. It will be used for the shortest path finding. It is an extension of Dijkstra shortest path algorithm. The extension here is that instead of using a priority queue to store all the elements, we use heaps binary search to store them. The A star search algorithm also uses a heuristic function that provide additional information regarding how far away from the goal node we are. This function is used in conjunction with the F heap data structure in order to make searching more efficient. Let us now look at a brief explanation of the A star algorithm. So, here is the explanation. In the event that we have a grid with many obstacles and we want to get somewhere as rapidly as possible, the A star search algorithm are our savior. From a given starting cell, we can get to the target cell as quickly as possible. It is the sum of two variables value that determine the node it picks at any point in time, and each step it picks the node with the smallest value of f, the sum of g and h, and processes the node or cell g and h is defined as simply as possible below. G is the distance it takes to get to a certain square on the grid from the starting point following the path we generated to get there. H is the heuristic which is the estimation of the distance to takes to get to the finish line from that square on the grid. Heuristic are basically educated guesses. It is crucial to understand that we do not know the distance to the finish point until we find the route, since there are so many things that might get in the way. In the coming section, now look at detailed A star algorithm. Initial condition: we create two lists, open list and closed list. Now the following steps need to be implemented. The open list must be initialized. Put the starting node on the open. Put the starting node on the open list if f at 0. Initialize the closed list. Follow the steps until the open list is not empty. First, find the node with the least f on the open list and name it q. Remove q from the open list. Produce q's 8 descendants and set q as their parent for every descendant I. If finding a successor is the goal, cease looking. Else calculate g and h for the successor. Successor g is equal to q into g plus the calculated distance between the successor and the q. Successor dot h is equal to the calculated distance between the successor and the goal. We will cover their heuristic to do this. The diagonal, the Euclidean and the Manhattan heuristic successor dot f is equal to successor dot g plus successor dot h. Step 3, skip the successor if a node in the open list with the same location as it but a lower f value than the successor is present. Step 4, skip the successor if there is a node in the closed list with the same position as the successor but a lower f value, otherwise add the node to the open list and for loop. Push q into the closed list and the while loop. We will now discuss how to calculate the heuristic for the node heuristic. We can easily calculate g, but how do we actually calculate h? There are two methods that we can use to calculate the value of h. First, determine h exact value, which is certainly time consuming, or second, utilize various techniques to approximate the value of h, less time consuming. Let us discuss both methods. Exact heuristic: although we can obtain exact values of h, doing so usually takes a very long time. The ways to determine h precise value are listed below. First, before using the A star search algorithm, pre-calculate the distance between every pair of cells. Second, using the distance formula, Euclidean distance, we may directly determine the precise value of h in the absence of blocked cell or obstructions. Let us look at how to calculate approximation heuristics. Approximation heuristic. To determine h, there are typically three approximation heuristics. First, Manhattan distance. The Manhattan distance is the total of the absolute value of the discrepancies between the x and y coordinates of the current and the goal cells. The formula is summarized below. H is equal to absolute of current cell x minus goal dot x plus absolute of current cell y minus goal of y. We must use this heuristic method when we are only permitted to move in 4 directions: top, left, right and bottom. Let us now take a look at the diagonal distance method to calculate the heuristic. Second method, diagonal distance. It is nothing more than the greatest absolute value of differences between the x and y coordinates of the current cell and the goal cell. This is summarized below in the following formula. D of x is equal to absolute of current cell x minus goal dot x. D of y is equal to absolute of current cell y minus goal dot y. H is equal to d into d of x plus d of y plus d2 minus 2 into d into minimum of d of x comma d of y, where d is the length of every node, default value is equal to 1, and d2 is the diagonal. We use this heuristic method when we are permitted to move only in 8 directions, like the king's move in chess. Let us now take a look at the Euclidean distance method to calculate the heuristic. The third method, Euclidean distance. The Euclidean distance is the distance between the goal cell and the current cell using the distance formula. So, h is equal to square root of current cell dot x minus goal dot x. So, now let us have the advantages of A star algorithm. The A star algorithm offers several advantages. Firstly, it guarantees finding the optimal path when used with appropriate heuristics. Secondly, it is efficient and can handle large search space by efficiently pruning unpromising path. Thirdly, it can be easily trolled to accommodate different problem domains and heuristic. Fourthly, A star is flexible and adaptable to varying width, cost or constants. Additionally, it is widely implemented and has a vast amount of resources and support available. Overall, the advantages of A star make it a popular choice for solving pathfinding and optimization problems. So, we have some disadvantages of A star algorithm also. So, here is the disadvantage of A star algorithm. While the A star algorithm has numerous advantages, it also has some limitations. One disadvantage is that A star can be computationally expensive in certain scenarios, especially when the search space is expensive and the number of possible paths is large. The algorithm may consume significant memory and processing resources. Another limitation is that A star heavily rules on the quality of heuristic function. If the heuristic function is purely designed or does not accurately estimate the distance to the goal, the algorithm's performance and optimality may be compromised. So, now we have come to the conclusion. In this chapter, we have understood an introduction to the powerful search algorithm, about A star algorithm. You then looked into the working of the A star algorithm and the pseudocode for A star. You finally saw how to implement the algorithm. So, in the next chapter, we will discuss about AO star search, where the best first search is what the AO star algorithm does. The AO star method divides any given difficult problem into a smaller group of problems that are then resolved. Using the AND OR graph concept, AND OR graph are specialized graphs that are used in problems that can be divided into smaller problems. The AND side of the graph represents a set of tasks that must be completed to achieve the main goal, while the OR state or OR side of the graph represent the different methods for accomplishing the same main goal. So, thank you for watching and we will see you in the next chapter.